Hi. In continuation to the previous presentation on maps and coordinate systems, this presentation is going to be on projections. At the end of the presentation, you should be able to understand why projections are important, what are all the distortions that can happen during the process of projections, and the classification of map projections, and what are all the common map projections that we are using in GIS. So, how do we define projections? Earth is more or less spherical, and the map that we are trying to draw are flat. So, the techniques that are required to represent a curved surface on a flat sheet is what we are trying to call it as projections. We have different map projections used in different parts of the world for mapping different sized areas and for different applications, which means that there are many different projections for different locations depending on the applications that we are trying to look at it. I can also define this projection in other words like the earth is divided into sectors by lines of latitudes and longitudes. This network is called as graticule. So a map projection denotes the preparation of the graticule on a flat surface. So the definition of the map projection is a systematic drawing of parallels of latitude and longitudes on a plane surface for the whole earth, or it can be a part of the earth, and it has to be drawn to a certain scale so that any point on the earth surface may correspond to that on the drawing. As I said earlier, we have different types of map projections. How to select the appropriate type of map projection for our study purpose? It's not a very easy task to flatten the spherical earth into a 2D plane where the earth has a lot of undulations, and bringing all the undulations, all the variable surfaces onto a plane is quite difficult task. Let us consider a basketball which is equivalent to that of a spheroid, and this basketball I want to bring it into a flat surface. So what are all the process that I do? I have to first deflate this ball, and then I have to tear it, and then I have to bring that into a 2D map. This process is what we call it as the projection. Okay. So what we try to understand here is there are different ways by which I can tear the ball. So the flattening of this spherical basketball into a flat surface, there are many different ways by which I can able to do it. While doing this process, we have a lot of errors that is called as the distortions in one or more of the following spatial properties. For instance, if the scale at any point on the map is same in any direction, then the shape of the object that is available in the spheroid earth is same as that in the map that we try to draw. So the conformal map projections preserve all the shapes. Very similar to that, we have distance or scale. It portrays distances correctly from center of projection. So this maps is called as equidistant maps where the distances are preserved. Equal area map projections preserve areas in the map that we try to draw. Similarly, the direction, angle or bearing where the azimuthal map projection preserves the true directions. So we cannot get all these kind of distortions free from a 2D map. The classification of map projection. There are an unlimited number of map projections that have been developed. The nature of these projections are so complex that they often possess one or more common properties. So there is no projection which can be grouped into single class. But on a general understanding, the variety of geometric projections can be classified based on the projection surface, which can be plane, planar, cylindrical, and conical. And based on the light source, it can be classified as genomic, stereographic, orthographic, and based on the projection orientation, it can be classified as normal, transverse, and oblique. For example, if you look at the projection surface here, the spherical earth is kept on the projection surface, which is conical, and all the objects on the earth is transferred into the sides of the cone, and then the cone is cut and you get the informations in the projected surface. So here the projection surface is cylinder, and all the objects in the earth is transferred into the cylindrical plane, and the cylinder is cut and then it is opened to get the projected information. Similarly, the projection surface here is planar, where the plane is kept at the required place and then the objects are transferred. Based on the orientation, how the map projections are classified is how do we keep the plane. So here you could see the plane is kept as a normal one. Here it is transverse and it is inclined, which is oblique. And you can also keep the cylinder straight, it's an oblique one, a transverse. Similarly, the cone surfaces can be kept, different orientations can be used to get the information of the earth surface. And based on the light source, how do we classify this map projection? Genomic. Here the viewpoint lies at the center of the globe, whereas in stereographic, the viewpoint lies at the opposite poles, and in orthographic, the viewpoint lies at the infinity point. And basically, map projections fall into four general classes, that is cylindrical projections, conical projections, azimuthal, zenithal or planar projections, and miscellaneous projections. Coming to the cylindrical projections result from projecting a spherical surface onto a cylinder. So look at this diagram. Here the earth is kept inside a cylinder and you have the latitudes and longitudes, that is the graticule, and all the information on the earth is projected onto the cylindrical surface, and then you try to cut open this cylinder and then you roll it off, you get a two-dimensional information of the earth. So if you use a cylindrical equal area projection, here we have the straight meridians and parallels, and the meridians are equally spaced and parallels are unequally spaced. And here the scale is true along the center line, and the shape and scale distortions increase near points 90 degrees from the center line. See, for instance, if this is projected, any object that is present here will be transferred exactly into this surface, whereas any object that is in the polar regions, the distance is not true as in the case of this object. So the advantage of the cylindrical projections are you get a continuous picture of the earth. That means the entire earth is covered in this cylindrical projections, and countries near the equator, you get the true relative positions. That's what I mentioned earlier. And area for most part is preserved here. And the disadvantage of this kind of a projection is the distance increases between the countries located towards top and bottom of the image. So that is what we were trying to understand. The view of the poles is very distorted. You don't get a clear view of this object in from this area. So you get a distorted view in both the polar regions. The next one is the conic projections. Conic projections result from projecting a spherical surface onto a cone. Now the difference between a cylindrical surface and a cone surface is the sides of the cones are tangent to the earth surface. That means only at one point the sides of the cone touches the latitudes. So that particular latitude where the sides of the cone touches, that particular latitude is called as the standard parallel. So it also gives you an indication that any object on the earth where this standard parallel coincides, which will be transferred truly, which means along the standard parallel all the scale is preserved. Whereas if you move away from the standard parallel, either on top or at the bottom of this cone, the distances of the object on the earth is not truly mapped into the conical surfaces, both in the north pole and in the south pole. So that is what it is given as: the area is distorted and the distance is very distorted towards the bottom of the image as the sides of the cone is moving away from the south pole. And how do we keep the cones or cylindrical surfaces? What are all the other ways by which we can keep these cones is you can also keep the cone cutting at 2 points, so you get two standard parallels, which means along the first standard parallel and along the second standard parallel you get all the informations that is transferred from the earth to the cone surface. And similarly you get a normal way of keeping the cylindrical positions. This is a transverse and oblique way of keeping the surfaces. So the standard parallels are keep on changing here. And the next type of projection is the azimuthal projections, which results from projecting a spherical surface onto a plane. So the entire earth is not captured into the plane. Whichever side we want to capture, only that area is projected onto the plane. So in this case, most of the distances are preserved, and the disadvantage here is only a part of the earth surface is visible. That is very obvious, and view will be half of the globe or less, and you cannot even get the half of the globe, and distortion will occur at all four edges because the distances from the edges to the object is far away when you compare that with the other locations. And the last type of projection is the miscellaneous projections, which includes unprojected ones such as rectangular latitude and longitude grids and other examples that do not fall into the cylindrical, conical or azimuthal categories. A map projection is not enough to define a projected coordinate system. We need some more informations like where is the center of projection, whether a scale factor is used or not. Knowing all these informations exactly for the projection parameters, the Earth can be projected properly. If you take map projections, it requires a point of reference on the Earth's surface. Most often this is the center or the origin. So this is the center or the origin of the coordinate system. As a result, the west side of this coordinate system, both the coordinates are negative. Here x is positive and y is negative. Here both the values are, both the coordinates are positive, and here you have a negative x-axis and positive y-axis. We try to use something called linear parameter, which is called as false easting and false northing here. Usually the origin of projected coordinate system is considered as the center point of the map to reduce all distortions. So the center point is the origin. This implies that our map has a negative value in this quadrant, which is on the west side of x-axis and south side of the x-axis. Okay. So false easting and northing values are usually applied to ensure that all x and y values become positive. For example, I take one of this axis from the origin, I take a new axis which is in the eastern side of the y at a distance of, let us say, 50,000 meters. And I also take another axis from the origin which is south of this x, which is also at a distance of 50,000 meters. So now my new origin is not located here. My new origin is transferred to this point, which means that there is no negative values which we earlier we had. Now all the points in the map is taken from this reference. So this is the new origin. Everything will be taken from this origin. So now I don't have a negative values because of this false easting and false northing. I avoided all the negative values for x and y coordinates now, which are all within 50 meters west of 50,000 meters west of y-axis and 50,000 meters south of x-axis. Similar to the linear parameters, we also have angular parameters. For instance, azimuth. Azimuth is the rotation of center line of a projection, and central meridian is the place where the origin of the x coordinate starts. The central meridian is synonymous to the longitude of origin or longitude of center. Similarly, central parallel is the origin of y coordinates, which is synonymous to latitude of origin and latitude of center. Standard parallel are the latitude lines where the scale is 1, which means there is no distortions. From the earth, whatever the object that we are trying to transfer it into the projection, it will have the true information. So that particular latitude is what we call it as a standard parallel. When we use a conical projection, there are two standard parallels, which we call it as standard parallel 1 and standard parallel 2. In both standard parallel 1 and standard parallel 2, we have this scale as 1, which means that there is no distortions. The other common map projections are, the first one is the polygonic projections. In a simple classic conic projection, we used a single cone to drape the entire model of the earth. Whereas in polygonic projection, we use multiple number of cones that are draped over the model of the earth. Each of these cones is tangent to its corresponding latitude, thereby making each parallel a standard parallel. So now you have to think of, like, if you have more standard parallels, more informations are transferred accurately. Half of these cones have their apexes over the north pole and half of the cones are reversed to have their apexes over the south pole in order to get more number of standard parallels. So this polygonic projection is a kind of projection that attempts to minimize all distortions while not eliminating any particular type of distortions. Hence, it may not fall fully into either conformal or equal area class of projections. And the next type of projection, common map projection, is the universal transverse Mercator projection. Transverse means rotated to 90 degrees. Mercator means it's a type of cylindrical projection. And universal means it has many number of projections, almost 60 types of projections is there. Universal transverse Mercator projection is used to define the horizontal positions. The horizontal positions means it is the XY coordinate system that is in 2 dimensions worldwide by dividing the surface of the earth into 6 degree zones. And the UTM zone numbers designate 6 degree horizontal strips extending from 80 degrees south latitude to 84 degrees north latitude. And UTM zone characters designate 8 degree zones extending north and south from the equator. And the origin of each zone is central meridian and the equator. That means the start point, the reference point, is the central meridian and the equator. And each zone that is divided in the UTM system, each zone has its own central meridian, and eastings are measured from central meridian with 50,000 meters or 500 kilometer false easting to ensure positive coordinates, and northings are measured from equator with 10,000 kilometer false northing for position south of the equator. Now this diagrams gives you an idea. The entire world is divided into grids, and you could see this is the equator, this line is the equator where it is set as 0, and this map is drawn between 80 and 84 degrees, and each zone is numbered like 1 2 3 4 up to 60. That's why the entire map is divided into 60 zones. East to west cells are labeled from 1 to 60 and centered over the Greenwich meridian. And you could also see the rows are named from C to X. So you have many number of zones in the UTM projection, and the north to south cells are labeled from C to X. And this is the overall picture of the UTM zones. So we have divided that into 0 to 60 grids, and it is from 80 to 80 south to 84 degrees north, and the equator is somewhere here. Okay, the entire zones are divided into 6 degree grids. So for example, if you take one of the grid, this is the zoomed part of one of the grid. So this grid, let us take, if you zoom it, when using UTM cell, the x-axis is called easting and y-axis is called northing. The unit of measurement is in meters, and along the center of the grid, easting is always set at 5 lakh meters and units reduced and increased on either side. This is because easting length changes due to the earth curvature. And this is an example of different zones. For example, zone 28P is somewhere, 28P is somewhere here, and 42H is somewhere here. So the zones, how the zones have been mapped. And this is the globe in which you could see the equator and the characteristics of the numbers, and this is the zone. When I say this is my zone, how we need to understand is 31R is the zone number, and this number indicates the easting, and this number indicates the northing. So you can able to identify in which zone you are trying to look at. So in summary, projection systems have been evolved to transform three-dimensional Earth into two-dimensional plane, and the choice of the projections are based on the purpose of the map and its analysis. So that is the end of the presentation. Thank you.